A very good morning to one and all present for today's class. And in the last class, we stopped at direct loading of a transformer, direct loading test of a transformer. So these are the list of tests that we are going to perform in the laboratory as well. So the tests are direct loading test, which is otherwise called as load test of a transformer. The other two are open circuit test and short circuit test. So we know obviously that the open circuit test of a transformer is we are not connecting any load in the secondary side of the transformer, and just by applying the rated voltage we are finding out current, voltage and wattmeter readings. Okay. So from these details we will measure what is the core loss of the transformer, because under an open circuit condition the copper loss of the transformer will be zero. The reason is when the transformer is open circuited, the current passing through the secondary winding and as well as primary winding will be very minimal. So at that time, so look at this. At the time, the copper loss are very minimum compared to core loss. The entire power which we are applying is utilized for magnetizing the core. So which is magnetic power, so completely a core loss component. Okay. So under open circuit condition, we are measuring core loss of a transformer. Okay. So look at this diagram. A single phase transformer, which is a auto transformer, is feeding the actual transformer that is to be tested. This is the transformer that we are going to do testing. So this transformer. Here, high voltage side is kept open and low voltage side is tested. In the last class, I asked you a question that why should we always perform open circuit test in the low voltage side? A few has answered me correctly. I'll tell you the reason why we are performing open circuit test in the low voltage line. Okay, so these are the reasons. Look at this. So from the open circuit, we are identifying what is the core loss of a transformer at a rated voltage. For example, if a transformer is given as, for example, look at this transformer. So this is, for example, a 200 volt and 2000 volts transformer, for example. So don't always stick with these values. The rating may be varying based on the size and design of the transformer. So I've given this for an example. So the transformer is having 200 volts and in the low voltage side and 2000 volts in the high voltage side. So the 2000 volts side is kept open. 200 voltage side is kept with the source. Okay. So we have connected a ammeter in series that will show you the no load current, which is I naught, and we have a wattmeter which will show you W naught, which is no load power, and this voltmeter will give you the no load voltage. Okay. So we know that under no load condition, the current passing through the secondary will be 0. I2 is 0. Okay. So what we are going to do in this test is we are going to apply the rated voltage, that is the rated voltage for this side is 200 volts. So I will apply a voltage using this transformer, this auto transformer, this side is called auto transformer. So when I increase the voltage by this auto transformer, this voltmeter, I will identify the value of increment from this voltmeter. So when the voltmeter's reading is 200 volts, I'll start this experiment. So by applying rated voltage, I'll do this experiment. Okay. So in case if I keep high voltage side in this side, what will happen? I should increase the voltage rating up to 2000 volts. Okay. In the lab setup, we will be having only 3-phase or single-phase transformers, auto transformers, which are able to develop only 230 volts or 415 volts voltage to the coil. Okay, so if you keep 2000 volts winding at this side, you need to apply 2000 volts, which is impossible because we are having a single phase supply, which is maximum give you 230 volts at AC RMS voltage. Okay, so the maximum capacity is 230 volts, but if you connect 2000 volts, what will you do? You cannot do that. You cannot increase the voltage up to 2000 volts because it is an auto transformer. It has its own limitation. It can develop only up to 300 volts or something. So based on its design, it can only pass a minimum voltage. So that is one reason. Look at this, the power source. That is what I told you. If low voltage side is preferred, the voltage to be supplied is less when compared to high voltage side. Okay. So from this example, we have 2000 volts here and 200 volts here. So giving supply to the 200 volts transformer is very easy for me, isn't it? So when I go for a lab test, I'll prefer this side. Open circuit test is done until the rated voltage. Okay, we are not considering about current magnitude here because the current magnitude will be very less in the open circuit test. The entire current given is going for magnetizing the core, so it will be requiring only very minimum amount of current. Okay, so that is the reason why we are not performing open circuit test in the high voltage side. Okay, and as well the meters, the measuring instruments what we have in the laboratory will be maximum of 600 volts. Okay, so for measuring 2000 volts voltage, we should have a voltmeter of about 2000 volts. Okay, that is also impossible for testing inside a laboratory. So we will require higher rated instruments. So that is also a reason. Okay, so these are the reasons why we are not using high voltage side for open circuit test. Can you understand? Okay. Next, I'll explain how to do this experiment. So we have to give the connections as per this circuit diagram. We have a AC source which is given in the which can be taken from the board that we are going to connect, and this is an auto transformer. So this supply will give you 230 volts fixed voltage. Okay. So from the auto transformer you can receive 0 to 300 volts. Okay, so I can vary the value of voltage from 0 voltage to 300 volt. So I'll explain the working of an auto transformer in later classes because that is coming under the module 2. So this auto transformer is capable of varying the voltage from 0 to 300 volts. So when I increase the voltage, output voltage of this auto transformer, the current will start to pass. Initially, it has to be started from 0, and current will be passing through the ammeter, wattmeter, and it will go to the winding, low voltage winding. So when current passes through this, I'll make a mark of this as I naught. Okay, so I naught will give me the no load current value, and W naught, the reading I observed from the wattmeter, is called as W naught, which is the no load power. This entire power is assumed to be core loss of the transformer. Okay, and this is the voltage of V naught, no load voltage. Okay, so the current passes here in series, it is in series, so this is also considered as I naught. So we are going to take only one reading. We are setting a 230 voltage from this, and we are confirming that 230 voltage from this wattmeter. Okay. And you can perform the open circuit test with the different voltage ratings, but the maximum permitted value is 230. Okay, you cannot go beyond 230. Set the value of 230 volts here. You can even take 130, but maximum is 230 is allowed. Okay, you are not considering current value here. So I get three different values, three different readings, which are I naught, W naught, and V naught. So I get these three values. I naught is no load current, W naught is no load power, and V naught is no load voltage. Okay. So that is what is given here. Rated voltage of transformer, input power, and no load current. So this no load current has two components, as I told you in the earlier classes. One is magnetizing component, and another one is working component or core loss component. This is otherwise called as working component. In some books, they would have mentioned this as working component, wattful component, and it is given with different names. Okay, IC means core loss component, IW means working component. Okay, otherwise they call it as wattful component. Okay, it is given with different names. Don't get confused. And this is the pure loss, the component which is responsible for the loss. And this current is the useful current, that is the current which is magnetizing the core. It is utilized for magnetizing the core. Okay. So from these data, so from these three data, I can identify the no load power factor of the transformer. How can I identify the no load power of the transformer? Is the wattmeter reading is given as V naught, I naught, cos phi naught. Okay. So from this equation, we know the value of V naught, I naught, W naught. So for measuring out power factor, no load power factor value, cos phi naught is equal to W naught divided by V naught and I naught. Okay. So for example, assume that you are getting a power of 300 watts. And voltage of 230 volts, a current of 1.1 amperes. Okay, so what will be the power factor? It will be 300 volts, 300 watts divided by 230 into 1.1. You will get some fractional values. If you find that value, you will get the power factor. So what will be the power factor value? Type of the power factor will it be leading, lagging, or unity? A transformer under no load condition is assumed as what? What type of load? So what will be the type of nature of the power factor? Lagging, leading, or unity? If I find the answer for this, I'll get a value, the fractional value 0.7 or something. Okay, will it be leading or lagging? I reduce the choice. It is not even unity. It will not be unity. 0.7 doesn't mean unity. You know that cos phi. If cos phi equal to 1, then we will call it as unity power factor. If it is 0.1, what will be? What it will be? Lagging. So don't think that sometimes you may be getting confusion that if power factor is 1.1, we will think this as leading. No, this is wrong. Okay. The power factor value magnitude cannot exceed 0.7. If you do the calculations properly, it will not exceed more than 1. So it will be 0.9, 0.95 lagging or leading. Okay. So we are just focusing on the phase angle between current and voltage. Either the phase angle may be leading or lagging. So the value will be less than 1 always. It cannot be, for a practical transformer, it cannot be equal to 1. So it will be either lagging or lead. So the answer is correct. Nitish Naveen has given the correct answer. It is lagging. Since the transformer under no load condition is assumed to be a pure inductive, so the lagging perfect, we are assuming it as the lagging perfect. So what we are measuring from the wattmeter is the iron loss. Okay, that is what given in the last equation of this slide. W naught is equal to Pi, which is called as iron loss of the transformer. The reason for assuming all the power measured by this wattmeter as iron loss is the current at no load test will be very minimum. Okay, so what will be the copper loss formula? What is the formula for copper loss? I square R. We know that. Okay, which is I square R. For example, if the current is 0.5 amperes, I require only 0.5 amperes of current. What will be the square value of this? 0.25. So resistance, for example, I assume the resistance value is 2. So what will be the loss? It is 0.5. So 0.5 watts is very less compared to the core loss component. Okay, so that is why we are ignoring the power, the copper loss at no load test. Okay, so the entire power measured by this wattmeter is assumed to be iron loss. Okay, so from this, look at this. This is what I derived in the last slide. W naught is given as V naught, I naught, cos phi naught. That has to be mentioned as phi naught, no load power factor. So cos phi naught is equal to W naught divided by V naught, I naught. Okay, so how can I identify phi naught from this equation? Phi naught from this equation, how can I derive? So which is cos inverse of W naught divided by V naught, I naught. Okay, so after getting the value of phase angle between current and voltage at no load condition, I can put this phi naught value at sine. Okay, so I will get sine phi naught value. Okay, after getting cos phi naught and sine phi naught, I can find out IC and IM value. What is IC? Core loss component. IM is magnetizing component. Okay, so just recall the equivalent circuit of a transformer. So just recall the equivalent circuit of a transformer. This is referred to secondary side. So what are the parameters we are checking here? Z1, R0, X0, R2, X2. That is Z2, and V1, V2, I2, and IA. Okay. So from this diagram, IC and IW values that also has to be found out. Okay. So this no load and load tests are utilized
are used to find out the equivalent circuit parameters of a transformer. Okay. So from the equivalent circuit, I'll first find out IC value and IM value using these equations. Okay. So IC is the current that is passing through the core loss component of the transformer. IM is the current passing through the magnetizing component of the transformer. That is the center branch of the transformer, equivalent circuit of the transformer. I'll draw it here. It's so that you can understand better. So this is R1, X1, X1, R0, X0, R2, X2, and the load. So this is the resistance of primary side, reactance of primary side, resistance of core loss component, reactance. This is denoted as R naught and X naught. Okay. And this is R2 and this is X2. And current entering is I1. This is V1. And voltage measured across the load is denoted as V2. The current passing through the core component is I0, and that current is divided into two parts. One is IC and another one is IM. Current passing through this is I2. So this is an equivalent circuit of a general transformer. Can you distinguish the each and every component from this diagram, because I used the touchpad of my laptop, so it will look messy. Can you find each component separately? Is it visible? Okay. Okay. So V1 is the supply voltage, I1 is the current passing through the primary, I0 is no load component, I2 is the current passing through the load. Okay. So we can write a current equation at this junction. I1 is equal to I2 plus I0. This is a general equivalent circuit of a transformer. So sometimes we'll draw the equivalent circuit refer to primary side or refer to secondary side. So and in that case, the circuit will be only the components value will be, the notations will vary. So if you refer the equivalent circuit from primary side, it will be denoted as R2 dash and X2 dash. If you draw the circuit referred to secondary, this will become R1 dash and X1 dash. So what I have drawn here is a general equivalent circuit of a transformer. Okay. So the current passing through primary side is I1. So since we have kept the secondary as opened in this test, I2 will be 0. So we may assume this part is open circuit. This doesn't have any components. Okay, so it is assumed to be this, that part, the right hand side part is neglected. So I0 is passing through the R0 and X0. Okay, one is IC, another one is IM. Okay. So for finding out IC value, we use this equation. For finding out IM value, we use this equation. Okay. So IC is passing through R naught. We know the voltage across this branch. So in parallel circuit, the voltage across each branch will be equal. Okay. So R naught and X naught are together connected in parallel across the supply voltage. So this is parallel to V1, isn't it? So the R naught is connected in parallel to V1 as well as X naught is connected in parallel to V1. Both of them have been connected in parallel. Okay. So we know the value of current, we know the value of voltage. So we can easily find out the resistance of core component and reactance of core. Okay. So R naught is V1. So that is now denoted as V naught since no load test is conducted. V naught divided by IC, the current passing through the particular branch. Okay. So this one is V naught divided by IM because through X naught component, IM current is passing. The voltage across that is V naught and current passing through that is IM. So X naught will be V naught divided by IM. So we are applying what theory here? Simply Ohm's law. What is Ohm's law? The equation of Ohm's law, V equal to IR. That is what theory we applied here. So I need R value, so it will be V divided by I. Okay, similarly here. Okay, so from this open circuit test, these are the parameters that we measured. Okay, so we measured IC value, IM value, R naught value, and X naught value, as well as no load power factor. These 5 values we are identifying. Okay, so that we have to put in the circuit diagram, equivalent circuit diagram. The next one is short circuit test of a transformer. Okay, so what is the result of open circuit test? We are finding out no load power factor, we are finding out core loss component, we are finding out magnetizing component, and R naught and X naught values. 5 data we are obtaining from the open circuit test. Okay. From next one is short circuit test of a transformer. Can you find out and tell me what are the differences you see here? So since I didn't mention any power value and values of meters, you cannot find any difference. Okay. So here I'll mention high voltage side and low voltage side. So can anyone tell me the reason why we are conducting short circuit test in the high voltage side? Can anyone pose the answer for this? So just I'll recall why we conducted open circuit test in the low voltage side. The reason is when we go for open circuit test, we will consider only on voltage magnitude. Okay, so building up a very high voltage in lab atmosphere is very difficult. For example, the transformer rating is 200 bar, 2000 volts transformer means developing 2000 volts inside a laboratory is difficult. Okay, that is the reason why we were going for low voltage side. Bringing out 200 volts from any source is easy. Okay, that will be readily available inside the laboratory. Without any power converter, we can get 200 volts. So that is the reason we were going for low voltage side while performing open circuit test. Similar reason here is in short circuit test, we will consider the current magnitude. Okay, so since it is short circuited, the secondary side is short circuited, we will perform this experiment up to the rated current of the transformer. Okay, for example, the transformer rating is 10 amperes. the maximum allowed current for this ammeter should be 10 ampere. We will not consider voltage value of this transformer. Okay, we are focusing on the current magnitude only. Okay, so I have given reason here. In short circuit test, we focus on calculating the copper loss. So open circuit test is utilized for measuring core loss of the transformer, and short circuit test of the transformer is performed to find out copper loss of the transformer. Okay, and thus we are thinking that the core loss is very less. Okay, high voltage rated current is small, and the reason this point. So look at the second point. High voltage, in high voltage side, the rated current is small. Why? So in the very first class, I told you when a transformer is stepped up, the current magnitude stepped up, the voltage is stepped up, the current magnitude will be stepped down. Okay, so the current magnitude of high voltage side winding will be less. For example, if it is 10 amperes, the current passing through this will be transformation ratio times of this. For example, if the transformation ratio is 10, the current in the low voltage side will be 100. Okay. Or if the, for example, if the transformation ratio here is 5, the current in the low voltage side will be 50. Okay. 5 times of 10, 10 times of 10. Okay. So 100 amperes, dealing with 100 amperes and 50 amperes is very difficult, and it is dangerous as well. You know that the effect of even the effect of 5 amperes can cause a huge damage to the winding and to the people who are dealing with the test. So we are doing the short circuit test in the high voltage side of the transformer. Okay. So I'll tell you the procedure how to perform this. So as well as same as that of open circuit test, we have a single phase AC source. We have an auto transformer of rating based on the size of transformer to be tested. So a small increase in the input voltage will cause huge increase in the current magnitude. So we are adjusting the auto transformer value up to the rated primary current value. Okay, now the high voltage side is assumed to be primary side of the transformer. So what is that? You have to find out before performing this test. You need to measure all the rated value. You need to find out all the rated values of the transformer. So this transformer, this example, I have put 10 amperes as rated value. So you have to increase this auto transformer. You have to adjust this auto transformer until you reach 10 amperes. So after this, you will get 3 details similar to open circuit test. Those details are VSC, ISC, and WSC. So what SC stands for? Short circuit. Okay. So short circuit voltage, short circuit current, and short circuit power. So I'll get all these 3 details. So these details are put here like in this equation. So from this equation, we are finding out the data which are R1E, Z1E, and X1E. So equivalent circuit, the total transformer is found. Okay, I'll explain how to find out all these parameters one by one. Okay, so similar to open circuit test, the power measured here is given as WSC is equal to VSC ISC cos 5SC. Okay, look at this notation. The notation has changed. In the previous case, it was W naught, V naught, I naught, and cos phi naught. Now, this equation, after performing short circuit test, this equation has changed as WSC, VSC, ISC, and cos phi SC. Okay. So here you are taking three different values. Even 10 amperes is 10 ampere is full load rated current. If you want to perform this test for half load, what will you do? I have given the rated value as 10 amperes. Okay, rated means for any electrical machine they will give a nameplate detail containing rated voltage, rated current, and rated power. If it is a rotating machine, they will give rated speed as well. Okay, so what is the rated current, rated values? How will you define rated values, and how will you define half of the rated value? What do you mean by rated values? I think I explained it already in the previous class. Can anyone answer what is meant by rated values? Are you listening? Rated value of any machine, how do you define it? Okay. So rated value of any machine is defined as the safe value within which we will get the machine operating in a safe manner. So beyond that values, for example, if the transformer rating is given as 15 amperes, beyond 15 amperes, if you are loading the machine transformer, the current, the high current passing through that coils may damage the winding. First step, that winding will get damaged. The work of a machine at maximum parameters at which the machine works at maximum efficiency. That is not the point at which the efficiency is maximum. So we can define the value, the parameter at which the machine works safely. The maximum value of the parameters, maximum value of any electrical quantity within which the machine is operating safely. That is called as rated values. Okay. So cos phi SE is short circuited power factor that is assumed to be full load power factor of the transformer. Okay. So in open circuit test, we consider that as no load power factor. And in short circuit test, we consider this as full load power factor. Okay. So from this equation, WSC in terms of voltage and current is given as VSC, ISC, cos phi SC. Okay, from this we are considering, we are measuring short circuit power factor, which is these two parameters are going in the denominator. The equation is wrong here. So cos phi SC is given as WSC divided by VSC into ISC. Okay, I'll rewrite this equation. We'll just look at this equation. So WSC divided by VSC into ISC. It is wrong here. I'll rewrite and post that slide in group. You'll check that later on. Now just look at this equation. This is the cos phi SC value. Okay, so I find out cos phi SC value, which is short circuit full load power factor. Okay, so as well, the power which is measured by the wattmeter is the total copper loss of the transformer. Okay, which is given as I square R loss. Okay, so this R I have assumed as total equivalent circuit of the transformer referred to primary side. Okay, which is I have given as R1E. Okay, so if you want to find out R1E value alone, This I square SC is going in the denominator, going to the left hand side and denominator. So I get R1E here. So what is the value of Z1E? Equivalent resistance, which is given as R1 plus X1E square. That is what is given here. Z1E is equal to square root of R1E square plus X1E square. Okay. Otherwise, it has been given as VSC divided by ISC. This current is depending on total impedance of the transformer as well. Okay. So from this equation, if I want to find out X1E, how will you find out X1E? Okay. So to take out this root value, I'll multiply the square times of this. So Z1E square is equal to, so take out of root, I have multiplied that again with the same value, R1 E square plus X1 E square. Okay, from this X1 E square is equal to square root of Z1 E square minus R1 E square. Okay. Sorry. X1E is equal to square root of Z1E square minus R1E square. That is what they have given here. Okay. So with these values, we have find out all the values of the equivalent circuit of the transformer. So the calculation of efficiency is given in this slide. From the open circuit test, we are measuring a power which is called as iron loss of the transformer. Okay. And from the short circuit test, what the power is measured using the wattmeter is copper loss at full load, because we are performing the test up to full load values of the machine. Okay. How will you identify a machine is fully loaded or halfly loaded? For example, you are performing a test in a generator, DC generator, which is capable of 20 amperes. Okay. So just look at, just listen to the example I'm giving. A DC generator is capable of delivering 20 amperes. The rated value of the DC generator is 20 amperes. Okay. I have loaded the DC generator with a lamp load of 15 amperes. So when I turn on every lamps connected in series or parallel, the current passing from the current absorbed from the generator is 15 amperes. What is the percentage of load I have done? Can anybody answer for this question? A 20 ampere generator is loaded 15 amperes. What is the percentage of load? 75%. Very good. So that means the transformer, the generator is 75% times is loaded. Okay. Similarly, in this short circuit test, we have conducted the test up to the rated current of the machine transformer. Okay. So it means it is fully loaded. So that is why they have mentioned it as FL. FL means FL stands for full load. So what you are measuring in the short circuit test is called as full load copper loss. Okay. So efficiency of the transformer. So these two are the losses. The output, say the efficiency of any machine is given as output divided by input. Okay. So input is further classified as or further defined as output plus losses. Isn't it? So we can write the input as output plus losses. Okay. So from these two test experiments, we are getting iron loss and copper loss. So total losses we have found. The other two losses, which is stray and dielectric loss, is very minimum. So we can neglect those values. So I consider only W naught and WSC. Okay, that is core loss and copper loss. Okay. So this is the output power equation V2 I2 cos phi 2 and V2 I2 cos phi 2 plus W0 plus WS. So this is the efficiency of a transformer that we find out using open circuit and short circuit test under full load condition. Okay, for example, if I want the efficiency of the machine at 75% of load or 50% of load, how will I change this equation? Is I'll multiply the fraction of load in numerator and denominator. The fraction of load is, if 10 ampere transformer is loaded only up to 5 amperes, the fraction of load is given as 5 by 10. So it should be mentioned in terms of decimal number 0.2. Okay. So it should be written in terms of 0.5. It is 1 by 2. The value is 0.5. So I should multiply that value 0.5 here with these values: input power, output power, and losses. Okay. So do you understand how to find out efficiency from open circuit and short circuit test? Okay. So I'll just recall it again. And this is the equation for finding out the regulation of the transformer using open circuit and short circuit test. This we have explained already while talking about voltage regulation. So I'll just go through this again so that you can easily understand. So open circuit test, we are performing the open circuit test in the low voltage side. The reason is we are performing this test up to the rated voltage. So rated voltage, if the rated voltage is small, it is easy to perform that in lab atmosphere. Okay. So in laboratory, producing a high voltage to test the transformer is difficult. So that is the reason we are going for low voltage side, open circuit test in the low voltage side. The high voltage side is kept open. So we are measuring, we are adjusting the auto transformer by up to the rated voltage. Keep always that in mind. Open circuit test is done up to the rated voltage. Short circuit test is done up to the rated current. Okay. And we are getting three different data, which are I naught, W naught, and V naught, using these meters, measuring instruments. Okay. And with the help of those values, we find out 5 different values. They are cos phi naught, no load power factor; IM, magnetizing component; IC, working component; and R naught and X naught. So totally 5 different values from the equivalent circuit we are identifying: R naught, X naught, and those 3 values: cos phi naught, IC, and I. Okay, so center branch is identified with that circuit diagram. So from short circuit test, we are identifying short circuit current, short circuit voltage, and short circuit power. So the wattmeter reading here is considered as the copper loss of the transformer, total copper loss of the transformer. Since all the other losses are very minimum, These two losses are identified with these experiments. Okay. So here we are measuring Z1E, X1E, and R1E. So with the help of that, we are measuring efficiency and regulation of the transformer. Do you have any doubt in this? It's up to regulation we are finding out. Do you have any doubt till now? If you don't have any doubt, just post no so that I will proceed. Okay. So next one is all-day efficiency. This question is repeatedly asked in 2 mark question. What is the all-day efficiency of a transformer? It's just the same as efficiency of a transformer, but if the transformer is working throughout a day, that is called as all-day efficiency. Usually, all the distribution transformers are working throughout a day, 24 hours. All the 24 cross 7, the transformer will be working. Okay, so it is just a definition. Output of a transformer in kilowatt hour for 24 hours divided by input of a transformer in kilowatt hours for 24 hours. So that is the all-day efficiency of a transformer. So it is measuring the efficiency of a transformer throughout a day. Okay, because in the power system, the load connected to any transformer or any generator by any power system is not a fixed one. Even you can take your house as an example. Uh, Always, your father may be telling you not to turn on the motor, the compressor, at evening time because the load will be very high at that time. So the currents passing through the transformer or any distribution panel will be very high. At that time, you again increase the load. It will consume more power, and that may cause some difficulty, some damages to the safety measures that you are having in your house. Okay. So at morning we'll be having very less power consumption. At evening we'll be having high power consumption. Even in a single day we are having this dramatic change. Okay. And also at night time we will turn on the AC. Uh, so the load will be high. And similarly, in summer, the power consumption will be very high compared to the winter season. We know the reason that during winter we will not put the fan in full speed and we will not turn on the AC. So in corporate, I'm telling this as your house as an example. Okay. So the load, what I coming to tell by this is the load is not fixed throughout a day. Okay. So we have to measure power in intervals and we have to measure the power in 24 hours time period and we are finding out efficiency for that. Then it is called as all day efficiency of a transformer. So this is the definition for that. Output of a transformer in kilowatt hour in 24 hours divided by input of the transformer in kilowatt hour in 24 hours. Okay. Many of you when writing these notations K, kilowatt, you are putting K in terms of capital letter. So if K is mentioned in capital letter, then it means Kelvin. Okay. So when you mention kilo, then it should be denoted as small letter. Okay. Lower cases. So next we'll see a small problem in this open circuit and short circuit test. So they have performed 2 tests. One is the open circuit and short circuit test in a single phase transformer. The test results has been given and they are telling us to find out approximate equivalent circuit of transformer. Okay. So read out this question. Obtain the approximate equivalent circuit of a given 200 volts per 2000 volts single phase 25 kVA transformer having the following test results. Okay. So they have told us to find out the approximate equivalent circuit. But I'm going to ask you which is the high voltage side and which is low voltage side. Look at the given data. which is high voltage side and which is low voltage side. 200 volts are, for example, I'll draw the circuit diagram. I'm not differentiating the transformer with number of turns. Okay, so here it is 200 volts. Here it is 2000. Which side is high voltage? Yes, 200 volts is. Nitish Navin, don't look at the test results. I'm asking from this value, 200 bar 2000. I'm asking from this value. And in which side? Okay, it is very obvious from the given data itself. You can see that 200 voltage is low voltage side and 2000 voltage is high voltage side. Okay. In which side they will perform open circuit test and which side they will perform short circuit test. So we have two parameters, right? So here you will get a terminal. In this side you will get a terminal. Okay. Which side you will perform open circuit test and which side you will perform short circuit test. You just explain, tell me LHS or RHS. LHS is left hand side we have 200 volts and right hand side we have 2000 volts. Which side I will perform open circuit test? I have to perform open circuit test. Can anyone answer? Right side what we are performing? Right hand side open circuit test, left hand side short circuit test. Is it so? Let's go to the previous slides. Look at this. So I should ask you this, like this. Which side will be kept open in open circuit test? Okay, I'll ask you like that. Which side will be kept open in open circuit side test? Right hand side or left hand side? So right side is kept open while performing open circuit test, and left hand side will be short circuited when performing short circuit test. So they have conducted all those tests, and the test results has been given like this. Okay, so open circuit test, they have given three values, which is 200 volts, 6 amperes, 350 watts. This necessarily not to be a maximum rated value of the machine. Okay, it is not necessary the given data to be rated value. They may stop the experiment at any instant and they will give you the value. Okay, the major advantage of conducting open circuit and short circuit tests is you can find out the efficiency of the transformer at any load condition, actually not loading the machine. Okay, so do you know the difference? In no load test, we are actually loading the machine, we are actually consuming the power, we are conducting as it is, how we are actually using the machine. Okay, but at that time we will waste the power. Obviously, while testing itself, we are wasting the power, isn't it? But open circuit and short circuit test consumes very less power compared to load test, actual loading. This open circuit and short circuit tests are consuming very less amount of power. So these are assumed to be efficient, but the calculation is tedious here. That is the only drawback of this. You can even write programs for this. If you give these details, who are all studying IT papers, I'll give you some programs for writing out, finding out the efficiency of a transformer. So these three values, if I put open circuit and short circuit results, the program will give me the result of final efficiency of the machine at any load and regulation of the machine at any load. Okay, so you can even write a program for that. So let us go to the problem. The given data, first write the given data. The primary voltage I have assumed taken in the low voltage side, 200 volts is assumed to be primary voltage here. You can even take 2000 volts as primary side, that is your wish. But you should be very clear, open circuit is done in which side. Short circuit test is done in which side. Okay. Secondary voltage is 2000 volts. Transformer rating is 25 kVA. Okay. So again, the open circuit test, the instruments are connected in low voltage side because the high voltage side is kept open. Okay. So what are the data given? Primary voltage they have given, which is 200 volts. So that value has been directly written. The 6 ampere. Excuse me. So 6 amperes is no load current and 350 watts is no load power. Okay, so we know no load power is given in terms of voltage and current as this V1 I naught cos phi naught. Okay, in our example we mentioned that as W naught. Okay, so from this value I need to identify cos phi naught first. Okay. So cos phi naught is P naught divided by V1 into I naught. So what is P naught value? It's just 350. V1 value is 200 and current value is 6. So we'll get cos phi naught as 0.2916. Okay. So from this equation, I'll find out the value of phi naught. How can I find phi naught? Phi naught is cos inverse of 0.2916. So what is cos inverse of 0.2916? I'll get a value. Okay. So let me check. Wait. We will ask Google for this since I don't have a calculator with me. That's cos inverse. Cos inverse of 0.2916. Which is 73.04. Okay. So I got 73.04 degrees. That means the current and voltage are lagging with this angle. 73.04 volts. Okay. So 04 degrees. So I put that here, sine of 73.04 is my cos sine phi naught. Okay, so I'll get value of this sine phi naught is 0.956. Okay, so let us find out the core loss component or watt-full component or working component. As I told you earlier, the core loss component is given with different names, so that I have mentioned all the values, all the names: core loss component, watt-full component, and working component. Okay, so IC is equal to I naught cos phi naught. We know that the equation is derived in the previous sections. So I naught value, which is given as 6 amperes, and cos phi naught value is 0.2916. Okay, so after multiplying this, I'll get IC. IC is 1.75 amperes. Okay, so the core loss component magnitude is 1.75 amperes. Next, we have to find out magnetizing component. What is the equation for magnetizing component? IM is equal to I naught sine phi naught. Okay, this is given us. So sine phi naught also we found out. Sine phi naught is 0.956. So I naught is 6. Sine phi naught is 0.956. After multiplying these two, I am getting a magnetizing current of 5.736. So with this two current, you just compare yourself. The current taken for magnetizing the core is 5 amperes, 5.7 amperes, which is almost 6, and this is 4 times the core loss component. Okay, so magnetizing current is higher compared to core loss component. Next one, we have to find out R naught value. What is the equation for R naught? Go to this equation. Look at here. R naught is V naught divided by IC. We know that what is value of V naught, what is the value of IC. So from this value, we can find out R naught value. So R naught is V1 divided by IC. Here I have mentioned as IW. Both are same. Don't get confused with IW and IM. Okay. Also I put that as IW. So IW. So 200 divided by 1.75, I get 114.28 ohms of R naught. Similarly, X naught is equal to V1 divided by this magnetizing current. V1 is 200 and magnetizing current, here it is mentioned as I mu. I'll put that as IM. 200 divided by 5.736, which is 34.86 ohms. So from the equivalent circuit, this branch I have completed. The center branch, which is mentioning the core loss of the transformer, I have completed, isn't it? So I have find out R naught value, I find out X naught value, I found IM value and IC values. Also we know that I naught is given in the problem. So this side is over. Okay. Next we have to find out the the other parameters like Z02 and Z0. Okay. So that is measured from the short circuit test. So these are the values they have given for short circuit test of a transformer. So short circuit voltage is 70 volts, short circuit current is 15 amperes, and full load copper loss, that is the meter measured value, 600 watts. Okay. Similar to that, From VSC and ISC values, we are identifying the impedance, total impedance of the transformer referred to high voltage side. Okay, which is given as V by I formula, which is derived from V by I formula. Z naught 2 is equal to VSC divided by ISC. VSC value is 70 and ISC value is 15, which is 4.66 amperes ohms. Okay, and R naught 2 is derived from copper loss equation. Okay, so WSC is ISC square into R naught 2. So I square R, using I square R value, they have found out R naught 2 value. So R naught 2 is equal to 600 divided by ISC square. ISC value is 15. So 600 by 15 square, which is 225, is equal to 2.66 ohms. So with the help of this, we can find out R naught 1 and X naught 1, because this test has been done in high voltage side of the transformer. We are going to draw the equivalent circuit referred to primary. So this, what we have got is secondary side voltage impedance and secondary side resistance. So I need to transfer this into primary side. For that I need transformation ratio. In the last class I explained you how to transfer, how to refer equivalent circuit parameters referred to primary and referred to secondary using this transformation ratio. Again I will explain that also. So transformation ratio is defined as the secondary voltage divided by primary voltage. Okay, the secondary voltage is 2000, primary voltage is 200. So the transformation ratio is 10 times. So with the help of this, Z01 is got using this equation, Z02 divided by K square. Okay, what is the value of Z02? 4.66. K square is 10 square, this is 100. So we'll get Z01 equal to 0.466. Similarly, R01 value as 0.02. So from these values, we know how to calculate X01 value. X01 is equal to square root of Z01 square minus R01 square. So the total is equal to 0.0382 ohms. Okay. So this is the final circuit diagram of the transformer, equivalent circuit of a transformer referred to primary, which is given as like this. Okay. So even you can mention the current values as well, IW and I mu. Okay. So this is how you have to draw. This question may be asked in 12 marks or 16 marks directly, and from the lab experiment you have to do all this. They will tell you to find out the equivalent circuit parameters of a transformer, and they will tell you to draw the equivalent circuit using open circuit and short circuit test. So this is how you have to identify all these values. R01, X01. Okay. Do you have any doubt? So don't log in from others' mobile or anything. Even if you log in from others' mobile, use your Gmail account to log in. After completion of the class, you can log out from that mobile. So while taking attendance, it will be difficult for us. Do you have any doubt in the previous problem? So next problem, similar to that, we are going to find out the approximate equivalent circuit of a single phase transformer, which is rated 400 volts per 4400 volts. And the test results has been given as 400 volts. Open circuit test result is 400 volts, 5.2 amperes, 600 watts. Short circuit test result is 155 volts, 50 amperes, 1850 watts. Okay. For this, we have to find out the approximate equivalent circuit. So after giving any problem, the first step you have to do is you have to find out, you have to write the given data. So we'll go one by one. The open circuit test result is given as this. Primary voltage, primary voltage is 400 volts. No load input current is 5.2 amperes and input power is 600 volts. Okay, the entire input is assumed to be core loss. I'll go through the. I'll just put the slides and you check it. So from the last equation of this, I'm finding out cos phi naught. Cos phi naught equal to P naught divided by V1 into 100, which is given us 0.288. So from that, I'm finding out sin phi naught. Cos phi naught. If you find cos phi naught, you can directly find sin phi naught. Okay. So cos phi naught, after finding out cos phi naught, find out cos inverse of phi naught. That will give you phi naught value. Put that for sin phi naught. Put that value with sin. So you'll get 0.957. Okay. So with the help of these values, you will find core loss component. Here the core loss component is 1.5 amperes. And from that 1.5 amperes, I find out R naught value. So we know that V1 is 400 volts. IW value, core loss component value is 1.5. That gives you 266.66 ohms. Okay. And wattless component, that is IM. Here I have mentioned that as I mu. IM is given as I naught sin phi naught. Phi naught value we measured from the previous one. So I naught is 5.2. Sin phi naught is 0.957. That gives you 4.97. So from IM value, I can find out X naught value. Okay. So V1 divided by IM is equal to 400 divided by 4.97, which is 80.5 ohms. Similarly, short circuit test is find out. So from that short circuit test, I'm getting Z02 and R02 values. Okay. So similar to that of a previous section, you're finding out the equivalent circuit of a transformer. Okay. So these two problems are similar to each other. If you have any doubt, please call me. Please ask me personally or you post your doubt in the group. Okay. Sumness test and polarity test, we will see that in next classes. So after this session, we may discuss the previous test we conducted in last classes. Wait, I'll take the questions.
Nagaraj sir,
சொல்லுங்க சார்.
chat boxல போட்டுருக்கேன் பாருங்க சார்.
ஓகே சார், I'll take. So can you see the questions? So the first question of first test is the lamination of transformer core is made of So all the answers may be looking similar. Cast iron, silicon steel, aluminum. We are obviously not using aluminum for any design, core design. Cast steel. So this question may be get confusing you. Cast iron, silicon steel, cast steel. These three obviously will be giving you confusion. Select silicon steel. Okay, many of you answered this question, and very few has answered aluminum. We are not using aluminum for core design. Alone or voltage and frequency. The third option is wrong. Frequency. Obviously, a transformer does not change frequency. I told you that in the first class itself. Frequency is not varied. The input and output frequency remains constant. Okay. And current transformer. When you think about a transformer, obviously you will say it steps up voltage, it steps up current, it steps down voltage, steps down current. Like that you will tell. Okay. But the true answer, the exact answer is the transformer transforms voltage as well as current. Okay. So the answer will be voltage and current. Third question, if the secondary voltage is larger than the primary voltage, the transformer is called as what? Secondary side voltage is greater than the primary side voltage. What type of transformer is this? The answers are, the given answers are negative transformer, positive transformer, step down transformer, and step up transformer. Okay, what will be the answer? Secondary voltage is greater than primary voltage. That is, in load side, I am getting higher voltages. So it is obviously step up transformer. The voltage is stepped up, the current value is stepped down. Okay, so you have to mention that as step up transformer. Based on voltage levels only, you have to tell the transformer, identify the transformer. Okay, so the question for the third question, the answer for the third question is step up transformer. We are getting higher voltage in the secondary side, so it is step up transformer. And the transformer rating are usually expressed in terms of, the given answers were volts, amperes, kilowatt, and kVA. What is the answer? Okay. So no machine is mentioned in terms of voltage and current. Okay, so the first two answers may not be right. Obviously, they are not right. And what could be the answer is either it should be kilowatt or kilovolt ampere. Okay, but I told you, unlike other electrical machines, the transformer is rated as kilovolt ampere. The reason is the losses of a transformer is depending on voltage magnitude and current magnitude. It doesn't look at, we are not looking at power factor. Okay, so the transformer rating is fully depending on voltage and current magnitudes alone. The total losses of a transformer depends on voltage and current magnitude. So the transformer rating is given in terms of kVA. Okay. The next question. So the answer for the fourth question is kVA. Fifth question. The value of flux involved in the EMF equation of the transformer. So what value we are mentioning? Can anyone recall the EMF equation of a transformer? It is 4.44. I need at least one answer so that I'll show you that in slides. So here it is. Look at this equation. The transformer output equation 4.44 at 5m into n1. So the flux mentioned here is maximum value of flux. So the answer will be maximum value for fifth question. Okay. So it is not the RMS value, it is not the average value, it is not the instantaneous value. So it is maximum value of flux. So this question is repeated. Material used for construction of transformer core is usually made of silicon steel. Again, it is repeated. A transformer core, next question, a transformer core changes AC to DC. Is it right? It doesn't change AC to DC. Transformer is not a converter. It doesn't convert power. Okay. So the first two answers, changes AC to DC, is not the answer. Okay. And the third option is it is step up or it steps up or steps down the DC voltages. In one class, I will explain to you a transformer. What will happen if a transformer is excited with DC supply? What will happen? If you give DC supply to a transformer, there will be no EMF induced in the secondary side, and the transformer core will get saturated. Okay. The answer is it steps up or steps down the AC voltages. So whenever if DC comes, you just eliminate that, omit the answer. The answer for that question is the transformer steps up and steps down AC voltages. Next question, the true or false type question. A transformer consists of two or more cores that are electrically coupled on a common core. A transformer is an electrical coupled device. Is it true? Are they electrically coupled? Nothing. So 3D nothing. False. Yes. The transformer is not electrically coupled. It is magnetically coupled, and it has a single core, but the core is laminated structure. The answer is false. The next question. If voltage is stepped up, the current is stepped down, and vice versa. That is, the voltage is stepped down, the current is stepped up. Is this true or false? The next answer is true. Nitish Navin has posted two, both false and true. Which should I take? Either false or true? Okay. So if voltage is stepped up, current magnitude is stepped down. It is true. Yes. A common method of cooling a power transformer. Still, I have not covered this topic. Common method of cooling is any book. You can use any of them. Natural air cooling, air blast cooling, and oil cooling. Since those topics will come under second module, so I'll teach them later. Okay, so you can put the answer as any of the above. Oil cooled transformer are there. Actually, in natural air cooling transformer is also there. Okay, so all the three methods are used for cooling a transformer. Second test is so we have just 1 minute. Within that, I'll try to cover that. The path of magnetic flux in a transformer should have high resistance, high reluctance, low resistance, low reluctance. Hello. Can you hear me? My call was disconnected. Okay. The path of magnetic flux in a transformer should have high resistance, high reluctance, low resistance, and low reluctance. Look at this problem. You can identify the difference between R1 value and R0 value. R0 is magnetic core path. Okay, so that is the major part within which the flux will be passing, isn't it? The core is the area where the flux is passing. Look at this equation. I'll show that here. Okay, so what is the value of R0? 266 ohms. Okay, and look at here, R0 1 value. This is the resistance of conductors. So what is the value here? It is 0.06, which is very small compared to R0 value. The reason for core to have high resistance is when core is having less resistance, more current will be passing through it. Okay. So first will be the answer. The flux path should be having high resistance so that it will carry a less amount of current and it will produce high flux value. And these questions I discussed many times. The power factor of resistive load is 0, 1, lagging or leading. 1 is right. The power factor of a resistive load is always assumed to be unity, so it is given as 1. Inductive load power factor is lagging, leading, 1 or 0. The inductive load offers lagging power factor. Similarly, capacitive load offers leading power factor. Okay, next one. What is the formula for R1E? That is equivalent resistance referred to primary. So it should have only the resistive components. Here the only equation that consists of resistive component is first equation, R1 plus R2. That is the only equation consists only resistive components. So other terms, look at this, look at the other terms, X2, that is reactive components. Is that one is impedance component. I1 and I2, obviously this will not be the answer. Okay. So R1E is equivalent resistance. E stands for equivalent resistance. 1 stands for referred to primary. Okay. So primary terms will be as it is R1. Secondary term will be in terms of dash. Will be given with dash, indication of dash, R2 dash. Okay. So first one will be the answer. Yes, right. Many of you are answering correctly. What is the answer for formula for R2E? So this is equivalent resistance referred to secondary side, which is again R1 dash plus R2. So if the question is given as referred to primary, you put the referred equation, the referred side as it is, R1. If it is referred to primary, put R1 as it is. Then R2 should be given with dash, R2 dash. Okay. And what is the formula for X2E? Yes, now they have asked the question. Equivalent reactance referred to secondary. So referred to secondary means primary side should be given with dash, X1 dash plus X2. Similarly, X1E is X1 plus X2 dash. So what is the formula for Z1E? Z1E is, it is impedance is the sum of resistance and reactance. Okay, so first is the answer. R1E plus X1E. And what is the formula for Z2E? Is similar to R2E plus X2E. So these are the answers of first two tests. In the next class, I'll give you, I'll explain what is some other tests of transformer. So we will finish the first module in next class. Okay. Thanks. Thank you for attending class. We'll see you in the next class.